Hello, my 12th standard warriors. Today we are going to discuss the topic of galvanometer. We're going to see how a galvanometer works. We're going to see what's there inside it, how is it used, what are the applications. All of this with me, your physics master teacher at Vedantu going live. And I'm Shreyas. You can call me Captain Shreyas. Hello everyone, welcome to the Pathfinder series. And this is one special topic. On demand, many students requested that, sir, we want to learn moving coil galvanometer. And there are times, there are instances where there have been some questions on this particular topic in JEE Mains as well as JEE Advanced. So I think it's a must that we must cover up this topic in the Pathfinder series on your favorite YouTube channel, We Enthuse. So We Enthuse is a dedicated English medium channel for all the students preparing for all the engineering entrance examinations. So welcome aboard, and I am Shreyas. I am the physics master teacher. I have been training kids for almost like a decade now. So welcome aboard. Hi Kaushik, hi Aniket, hello Shruti, hello Bomwathu. Wow, what a nice name. Hi Islamic Media, hello Kaushik, David, Sahil, hello D-Dad. Hello Litashri, welcome Abhinav, hello Shirley, hello King, nice to see all of you. Good evening. So let's get going and let's first see how a galvanometer looks like. Some of you might not have seen it, some of you might have seen it but not realized that, oh, that's a galvanometer. So basically a galvanometer looks something like this. You will see two terminals over here. Yeah, you can see some two terminals over here. You will see a needle over here. You will see a scale, and you will see one positive side and one negative side. So how many of you have seen a galvanometer? Let me know in the chat box. Okay, come on. Hi Jacob. Hello Ashika. Welcome. Nice to see all of you here gathered with high Josh and high spirits. Yep, in the lab, definitely. Okay, so Litashri, this is how a galvanometer looks like. Now, once we know what a galvanometer looks like, okay, Shruti has seen it, David has seen it, Abhinav has not seen it, Cholan has also seen it. So, then thing that we need to talk about is, what exactly does a galvanometer do? So, see, first of all, understand a galvanometer nothing but measures current. Galvanometer does not measure voltage. What does it measure? It measures current. But it does not measure huge amount of current. It actually measures very small amount of current. So you saw those two terminals. So when you pass current through it, then it measures how much current is flowing through it. It deflects when there is current. If there is no current, there is no deflection. If there is current in the opposite direction, the deflection is on the other side. So if the current passes this way, it deflects on the positive side. If the current passes the other way, it deflects on the other side. And if there is no current, obviously there is no deflection. So that's what it does. Now, the most important relationship that we are going to prove today is this one, that the deflection theta is directly proportional to the current inside the galvanometer. So that theta, which is the deflection, is going to be proportional, and we are also going to find the constant of proportionality. You might have used this in the construction of voltmeter and ammeter. So this was the basic principle, but we're going to prove this and we're going to see the interesting theory behind it. Why is the deflection proportional to the current? Why is it not inversely or square proportional to the current? We're going to see that. Okay, so very important relationship that we are going to study today. Okay, now remember, every galvanometer has a particular limit, and that is called as the full scale deflection current. That means when the current passes, the needle deflects, but there is a limit till which it can deflect. Beyond that point, what will happen is most likely the galvanometer is going to burn out because of that excessive current and excessive heating. So there is always a full scale deflection. You will see the needle cannot deflect beyond that point, and even if the current can flow, most likely it is going to burn that coil. So that is called as the maximum deflection current or the full scale deflection current. So when this happens, you will see either it will burn out, okay, or the needle is at the maximum limit. Okay, that's what it is. Now this is very important Because you should make sure all the instruments or the wires or the connections around the galvanometer, make sure that the current in the galvanometer should never exceed this maximum current. So the current inside the galvanometer should always be less than or equal to this maximum full scale deflection current. This is how you will always use the galvanometer. Yeah, very, very important. Okay, so I hope everybody is clear about this. Moving ahead to the next pointer. Now this is very, very interesting. Balaji, just join in. You have missed a couple of minutes. Ishwara, join in. I think you too have missed a couple of minutes. Okay, you too have missed a couple of minutes. But you can go back as a replay and you can definitely watch it. How to find Imax? Okay, it's very simple. Because, see, how do you find Imax? You can find it either experimentally, like you have to burn out few coils, or you have a dial. Okay, you know that your dial can take up from 0 degrees to, let's say, 90 degrees. This is, let's say, 45 degrees. Example. You know that it deflects, for example, 1 degree for 1 milliampere. It deflects by 1 degree for 1 milliampere. So for 90 degrees, it will deflect by how many milliamperes? 90 milliampere. So that's the easy way to figure out, what's the full scale deflection current. Second way is, it can be given to you experimentally that they pass different currents and they figure out, oh, this is a maximum current that you can pass, and accordingly you make markings on the scale. So either ways you can get it. I hope that makes it clear. Vanakkam Zayed, Vanakkam, hello Rakesh, join in Bachalog. Yes Surya, I can see your message. Yep. So you have seen galvanometer and voltmeter. Exactly. That brings me to the uses of the galvanometer. So galvanometer can be used as either a voltmeter or an ammeter. So when you make sure that the value of the current in the circuit by connecting it in parallel to a low resistor, and you can also measure the voltage by connecting it in series with a high resistance. You might have seen the use of galvanometer as a voltmeter, as an ammeter. So for example, if this is a circuit, then you place a galvanometer and you have a shunt resistance. So this is your shunt resistance. That's it. This will make it a ammeter. So this is an ammeter. That's it. That's what an ammeter is. And similarly, a voltmeter is nothing but you have a galvanometer and you have a very large series resistance. So this is a resistor in series, and it is. So what I was saying was, okay, great. So what I was saying was, the zero of a galvanometer ideally should be at the center. You will have one positive side and negative side, but you can have some specially designed galvanometers where zero is at the corner, and then you know for a fact that the current only flows in one direction. Then you will only have the positive side of the galvanometer. Now that will be a special kind when you know that the current is not going to change the direction. So yes, both are possible. Technically, both are okay and correct. Okay, there is nothing wrong in that. All right. Now, moving ahead, construction of a galvanometer. What are the different parts of a galvanometer? Very, very important. So first, you will see that there will be a dial, there is a pointer, you will see there is a coil. Okay, you can see that there is a coil over here, this is a pointer, this is the scale or the dial, you can say, and then you have this spring over here. Yes, this is a coil, these are two magnets. This coil can turn, and that coil is directly attached to the needle. If the coil turns, the needle will also turn. If the coil bends that way, the needle will turn that way. Okay, and it is hinged, it is supported on an axis, and that axis is connected to a coiled spring. Yeah, there is a coiled spring over here. You can see that there is a spring over here. So that spring will make sure that the pointer or the needle comes back when there is no current. When you pass current, the needle will deflect, the coil will deflect. But when there is no current, you will see the spring will pull it back. It is like a restoring torque. So it provides a restoring torque to bring it back. Okay, and then you have these magnets, you have this pointer, and you also have the mirror. Can somebody tell me what is the use of a mirror on a galvanometer? Is it to see your beautiful face, or is it to see something else? What is the use of a mirror on a galvanometer? It's a very interesting thing. I'll tell you what. See, just imagine this. If there are these markings like 0, 1, 2, 3, and this pointer is here. This pointer is here. So if you see directly in front, then you might see that the needle is just in front of 2, if you are directly in front. But if you go little bit on the side, then you will feel that the pointer is between 2 and 3. If you see it from here, then you will feel that it is between 1 and 2. So when you have that mirror, no, it's not for magnification, it's not for big size, it's basically to avoid parallax. So if you cannot see the reflection of the needle, see, the needle will have its image. If you cannot see the image of the needle, that means you are seeing it properly. But if you see it sideways, then or from this side or from this side, then you will be able to see the image of the needle, then that means you are not seeing it properly. Is that clear? Is that clear, my warriors? Think about it. Have you understood it? What happens when you see the image? That means you are seeing it from sideways. When you cannot see the image of that needle, that means you are seeing it properly directly in front of it. So it is to avoid the parallax effect. Correct? Yep. Okay, chalo, let's get moving to the next one. Okay, now that you know the basic construction of a galvanometer, how does it exactly work? How does it move? So we are going to come to that, but let me tell you a very important thing. You can download the entire PDF. I have explained the construction of a galvanometer in this particular passage, in this paragraph. You can download it by joining our Telegram group. So go ahead, join the Telegram group link so that you can download the entire PDF. You will need this for your CBSE boards or board examinations. Okay, so go ahead, join the Telegram group link to download the PDF. Alright, now what exactly happens? Let's try to work this out. So first of all, there are two main concepts in a galvanometer. If you understand these two concepts, we are going to combine them together and then we'll actually see the formula, okay, for different things. The first thing is that when a coil of area, let's say A, turns, let's say N, carrying current, okay, it carries current, let's say I, is placed, okay, it is placed in a magnetic field. Okay, if it is placed in a magnetic field, let's say B, what will happen? It will experience, what will it experience? A torque. It will experience a torque, and that torque is given by MB sine theta, where M is nothing but NIA. So number of turns into current into area into magnetic field into sine theta. So that is the value of the torque which a coil experiences when placed in the external field. That's the first concept. The second concept is the concept of a torsional spring, a spring which is twisted. So whenever you take a spring, okay, you can extend it, you can compress it, then there is a force which will, prevent its extension or its compression. But when you twist a spring, then there is a torque which will try to restore it back. Okay, so there is a torque which will try to restore it back to its original position. So the restoring torque, of a torsional spring. Torsion means twist. This meaning is basically twisting spring, a spring which is twisted. Torsional spring, okay, which is rotated, okay, which is rotated by theta, is given by tau is equal to C into theta, where this C is called as the torsional constant, twisting constant. Just like you have a spring constant, you have a torsional constant. Some books use the symbol K or capital K or kappa and different things. So what is theta? This theta over here is the amount by which you twist the spring. This theta over here is the angle between M and B vector. So if you are wondering what is this angle theta, it is the angle between the area vector and the magnetic field vector. So you will see that the coil will have some area vector and there will be magnetic field like this. So that angle is basically theta. Is that clear, my warriors? Is that clear, my warriors? No main, you can check out the link which is there in the description box, and that's how you can join the 2022 crash course, but it has not yet started. Okay, it will start in a couple of weeks. As soon as it starts, we'll definitely announce it. Okay, so two concepts. First concept, the torque due to magnetic field is NIAB sine theta. Theta is the angle between area vector and magnetic field vector. And when you twist a spring, the torque to restore it back is given by C theta. What is C? The torsional constant. Every spring has a torsional constant. Keep this in mind. Alright. So, having said this, let's move ahead. And all of this you will get it in the PDF as well. Don't worry. Now, apart from these two concepts, there is one very minute concept which is also used in a moving coil galvanometer, because of which it works the way it is. And not many people know about it. Let's talk about that. There is a special way in which the magnets have been cut. You do not use a bar magnet. These magnets are often called as cylindrical magnets. Reason for them to be called as cylindrical magnets is, see, when you have the north pole and the south pole of a magnet, then the magnetic field lines look somewhat like this. These are the field lines between the north pole and the south pole. But when you want a field in such a way, that the field lines looks as if they are going towards the center of this circle. Look at this, the field lines go like this, the field lines come from here. That is called as a radial field. This field is non-radial. Obviously, it's not directed towards the center, so that's why it is called as a non-radial field. Radial field means the field lines go like this, come out like that. The field lines go like this and go like this. Field lines come from here, go like this. Field lines come over here, go like this. Field lines come over here, go like this. So this is how the field lines look like. Now if you observe, they all feel as if they are going towards the center or they are coming out from a central region. This is basically a radial field. And how do you get a radial field? You need a magnet which is curved in a peculiar way, and that is basically a cylindrical form. It's curved. You can see this is the north pole, you can see this is the south pole. When the magnets are in that curved form, then the field which comes out of it is radial in nature. Is that clear? Is that clear, my warriors? Think about it. Yes, Kaushik, I'll definitely inform regarding the JEE 2022 crash course as soon as it is launched on YouTube. Don't worry about it. For now, let's concentrate on the class. Yep. Okay, clear, my warriors? So this radial field is very important for the construction of a galvanometer. Without radial field, you will not get a galvanometer. So how do you, what is the use of a radial field, one might think? Let me get to that point. Okay, so we have a cylindrical magnet. There is a radial field over here, and now let's see what exactly is happening. Think, let's say the coil right now is over here. Okay, this is the area vector of that coil. Okay, this is the area vector of the coil. Okay, everybody think about it. Now look at the magnetic field lines. There is a cylindrical magnet over here. Let me just probably draw it over here. This is the cylindrical magnet, north pole and the south pole. This is north, this is south. Okay, this is north, this is south. Now, how will the field line look like? A field line which will be cutting through the the axis will look something like this. This is one field line which will be going like this. Okay, this is the field line which will be passing through the coil. Okay, this is the magnetic field line. Let's take some other orientation. Okay, let's take some other orientation, maybe like this. So right now the area vector is this way. Okay, now these are your cylindrical magnets. This is the north pole, this is the south pole. Think which field line will be cutting through the coil. So I think there will be a field line which will be going like this, and it will be going like that, and there will be another field line which will be going like this and going like that. I am interested in this part because this side of the coil will be, influenced by this magnetic field, and this side of the coil will be influenced by this side of the field. It's as if, saying, you had a field line which went from here to here, right, from here till here. Okay, so think of a field line which went from here to here. I know it is getting discontinued, but whatever happens here will not influence the coil because it is not touching the wire. I'll repeat again. This field line, this red field line is not actually touching the wire, the black coil, it is not touching it. So it will not apply any force. So this part, this part, this part are not intersecting that wire. So the only part which will influence or cause any force on the wire is this field and this field. Okay, take any other orientation. For example, let's say it is like this and the area vector is this way. You can always think of some magnetic field which will probably, go like this. It will go like this and it will be coming out from here, but this part is not important. And some other field line will be coming from here and it will be going like this. So always you will see that there is a magnetic field line which is in the plane. You will see that there is a magnetic field line in the plane of the coil. Are you able to see that? Are you able to see that, my warriors? There is a B field. There is a B field in the plane of the coil always, no matter which orientation you take. If you take this orientation, there is a field line here. If you take this orientation, there is this field line over here. If you take this orientation, you can see there is a field line over here. Always there is a field line in the plane of the coil. That means that the area vector is always perpendicular to the field in any orientation. The magnetic field line is always perpendicular to the area vector no matter which orientation you take. That means that the torque which is acting due to the magnetic field will be N, number of turns, current which is flowing through the coil, A, which is the area of the coil, into B into sine, because it is perpendicular, it will be sine 90. So it will be just NIAB. That's very, very important. See if you guys got it. So irrespective of the orientation, the torque remains independent of theta. This is the torque by the magnetic field. So what is the torque indirectly proportional to? It is directly proportional to the current. Think about it. More current, more torque on that coil. So it is not dependent on the angle theta. Is that clear, my warriors? This is the most important concept over here. So the cylindrical magnets created a radial field. So no matter what the orientation of the coil is, you always see there is a field entering, field exiting, field entering, field exiting, field entering, field exiting. So always there is a magnetic field in the plane of the coil. And when there is magnetic field in the plane of the coil, area vector is perpendicular to the field, and that's the reason why this theta is always 90. So the torque is always NIAB. That's it, as straightforward as that. Very, very important. Okay, once you get this, the next thing that you should understand is the torque by the magnetic field is always NIAB, which let's say rotates it this way. If there is torque, obviously it will start rotating, but this entire coil which is suspended on that axis is also attached to a spring. So the moment this magnetic field tries to rotate that coil, the spring will create a restoring torque. The more you rotate, it will be more difficult for you to rotate it because the spring will create a restoring torque. So as the coil turns due to the current, and B field, the rotation, that rotation is opposed. Who is it opposed by? It's opposed by the spring over there. So that spring will create a restoring torque. Finally, both these torques will balance each other and the needle will come to a halt. So you have passed some current, the needle deflects, and at that point where the restoring torque by the spring balances the magnetic field torque, there it will come to rest. So at equilibrium, I can say the torque by the magnetic field will be equal to the torque by the spring, which is the torsional spring. What is the torque by the magnetic field? It is NIAB. What is the torque by the torsional spring? Well, that is C into theta. Remember, I just told you it is C theta. That's it. You just need to use that and you'll get the answer. Now look at this. Theta will be equal to NBA divided by C into I. That will give me the final answer. Theta is NBA by C into I. This tells me that theta is directly proportional to the current. This is exactly what we wanted to prove. This is exactly what we wanted to prove. That's it. So theta is NBA by C into I. Done, done, are done. Now there is a very easy way to remember this. NBA. NBA. Remember basketball. NBA is, yeah, like basketball championship. So remember that word NBA or those alphabets or the tournament were related to basketball. It's then very easy for you to remember it. NBA divided by C. That's it. Done, done, are done. Okay. So more the current, more is the deflection. So that's where it comes to a halt, where the restoring torque of the spring balances the torque by the magnetic field. Now, based on this result, okay, I have put up all these derivations out here. Don't worry about it. It will be available for you in the PDF. There are few other formulas which you need to know. Few other formulas. What are the other formulas? One is the current sensitivity. What is the meaning of current sensitivity? Current sensitivity means how much does it deflect per unit current. We just saw that theta is nothing but NBA divided by C into I. How much is the deflection per unit current? That means bring this I below. So theta by I will be nothing but NBA divided by C. This quantity over here is called as current sensitivity. So the unit of that will be either in degrees per ampere or radians per milliampere, anything. You can use some unit of angle upon some unit of amperes or current basically. Okay, so that's what current sensitivity stands for. How much does it deflect per unit current that you pass through it. The second thing that you need to remember is the voltage sensitivity. See, remember this. Okay, forget all this. Any galvanometer coil will have some resistance. It will have some resistance. Hi Raghavendra, welcome. Good evening, bacha log. It will have some resistance. So, if that coil has some resistance, when you pass some current through it, obviously some voltage will be developed across it. So, what is the voltage which is created? And how is it related to the angle? So the angle per unit voltage is nothing but the voltage sensitivity. Now that is very easy to remember again. Think, voltage sensitivity will be nothing but the angle by which it deflects per unit voltage. Now voltage by Ohm's law is IR, correct? So it will be theta by I. V is IR, so this IR will come in the denominator, but this theta by I just gave you. What is theta by I? It was nothing but NBA divided by C, and this resistance just comes over here. So that's it. So the voltage sensitivity will be nothing but NBA by CR, that resistance comes below, because you have to take into account the Ohm's law. So from here to here, it's nothing but Ohm's law. Okay, and what is the unit of voltage sensitivity? Again, it will be in radians per ampere or degrees per milliamperes, whichever you want to use. That's it, as simple as that. So that's voltage sensitivity of a moving coil galvanometer. The last thing is the figure of merit. You will have questions on figures of merits as well. Gautam Spring, I have taught kinematics way back. Check out the playlist. It's already done, bacha. We are already in rotational mechanics. So go check out the playlist. You will see 1D kinematics, 2D kinematics separate. It's already done. Hello Mani, welcome, good evening. So what is figure of merit? It's basically inverse of your current sensitivity. I'll tell you how. It's defined as the deflection current, the ratio of the deflection current and the number of graduations, or basically the angle by which it deflects. Basically what it means is, the figure of merit is nothing but the full scale deflection current divided by the maximum angle by which the needle gets deflected. Now if you think about it, current is always proportional to theta. So this ratio will also be equal to any current upon any theta, and this ratio is nothing but 1 upon current sensitivity. Think about it. Current sensitivity was angle per unit current. So this is nothing but 1 upon current sensitivity. That's it. As simple as that. So figure of merit is basically inverse of current sensitivity, or the way it has been defined is the maximum current which can be passed upon the maximum angle by which it gets deflected by. That's all. I hope that is clear. So all these definitions, if you are clear with, I'm pretty sure you'll be able to solve some questions. Let's solve some 3-4 questions at least over here today. So the first question is up on your screen. There is a galvanometer which is used in laboratory for determining the null point in electrical experiments. When you pass a current of 6 milliamperes, it produces a deflection of 2 degrees. What is the figure of merit close to? Let's see how many of you can get. Okay, come on. Think carefully. What will be the figure of merit? I just told you what the figure of merit is just some time back. It was nothing but the maximum deflection. It was nothing but the maximum current upon the maximum deflection. Just use this fact and I'm pretty sure you will be able to get it. Come on my warriors, think about it. What should be the correct answer? I just told you about it, and I told you current is always proportional to theta. So you need not take the maximum current and the maximum deflection. This ratio will also be similar to any current upon that particular deflection. And I think I know that the current which is passed is 6 milliamperes. That means 6 into 10 to the power minus 3 upon theta. What is the angle? That is basically it produces a deflection of 2 degrees over there. Okay, so 2 degrees over here, that is 1 division. So 6 by 2 is nothing but 3 into 10 to the power minus 3. That's the answer. Yep. So 3 into 10 to the power minus 3 ampere per division, because 1 division is 2 degrees. That's it. Done. Okay, perfecto. Moving on to the next question coming up on your screen. Here it is. Okay, a moving coil galvanometer has a coil with 100 turns, area of pi centimeter square. There is a torsional spring constant 10 to the power minus 6. The coil is placed in a magnetic field parallel to its plane. When the coil deflects by 1 degree for a current of 1 milliampere, what is the magnetic field approximately equal to? Let's try to figure this out. Okay, so first of all, I think I need to go with my formulas for the galvanometer, and the standard formula that I told you is NBA divided by torsional constant into current will give you the angle of deflection. I think I know most of the things. The only unknown is B. So the value of B will be C into theta. Okay, C into theta. Everything else will come below. N will come below. A will come below. Current will come below. Now it's just a matter of substituting all these values. So what is the value of torsional constant? Torsional constant is 10 to the power minus 6. What is theta? Okay, theta is 1 degree. Be careful. 1 degree. How much radian is 1 degree? Think about it. Come on. What are you going to do? So first thing that you need to do is, pi radian, okay, is 180 degrees. So 1 degree is how much? Pi? Yeah, come on. Pi by 180 or 180 by pi? Yes. Okay. So 1 degree. So 180 degrees is pi radian. So 1 degree will be nothing but pi by 180 radian. Okay. Perfecto. Now what you need to do? You just need to put the value of theta over here. Okay, just need to put the value of theta over here. And what is that theta? Theta is pi divided by 180, and over here number of turns. What is the number of turns? It is 100. What is the area? It is pi centimeter square. that means into 10 to the power minus 4. Okay, the area is pi into 10 to the power minus 4 in meter square. So that is one thing. And the current, how much is the current? The current is 1 milliampere. That means 1 into 10 to the power minus 3, amperes. So just do the math, you will get the answer. Okay, it's just a matter of substitution. Aren't these problems very easy now? Okay, so if you know this formula, this is the basic formula, you will get the answer. As simple as that. Okay, so it's just a matter of calculation. Okay, most of you are saying D. Yes, it should be D. Okay, it should be D. Correct. Yes. Great. Moving on to the next question. Here it comes. Okay, let's see how many of you can do this. There is a current sensitivity of a moving coil galvanometer and it is 5 divisions per milliampere. Current sensitivity is 5 divisions per milliampere and its voltage sensitivity is 20 divisions per unit voltage. Then the resistance of the galvanometer is how much? Very interesting question. Let's try to figure this out. See, current sensitivity means, let's say this is sensitivity of current, means the angle by which it deflects per unit current. Voltage sensitivity means the angle by which it deflects per unit voltage, right? That's what it is. Now, from this, what I get is current is theta by SI, and from this voltage is theta by SV. Fair enough? Now, using Ohm's law, what I get is, since V is equal to IR, I need to find out the resistance of the coil. Just use these values, use these formulas over here. Voltage will be theta by SV. Current will be theta by SI into R. Theta will get cancelled. So you will get resistance is SI by SV. That's it. You got the value of resistance as SI by SV. So it's current sensitivity by voltage sensitivity. So let's substitute all the answers and the values and see what do we get. Sensitivity of current. What is the sensitivity of current? It is 5 divisions per milliampere. So when you convert it into amperes, it will become 5 into 10 to the power 3. Because per milliampere it deflects by 5 divisions. So if you pass 1 ampere, which is huge, so it will deflect by 1000 times more, which is 5 into 10 to the power 3. That's your current sensitivity. What is voltage sensitivity? It is 20 divisions per volt. So just put 20 over here. So this will be nothing but 5000 divided by 20. So it will be 500 divided by 2, which is nothing but 250. 250 is option A. Done, done, are done. 250 ohms. Correct. Very good. Correcto. Welcome. Excellent. So that's the answer. Yeah, option A is correct. So this is another question which you can solve it for homework. I'll put up the solutions in the Telegram channel link. Okay, so just join the Telegram group. Make sure you are in it so that you will be able to download the PDF and also check the solution. But leave the answer in the comment section below once you are able to solve it. And if you are interested in the pro subscription for the crash courses, for KVPY courses, for CBSE term preparation, for long-term preparation, for test series, for academic mentors, then go ahead, check out the link which is there in the description box below. And the courses start for as low as 1,530 rupees per month, which is very, very affordable. You have to use my coupon code, obviously SHHPRO, to get the 10% off. And if you are interested, you can go for classic and plus version, because most students generally go for the classic version where you get doubt solving on the mobile app, and on the plus version you get your personal mentorship. So I hope you have enjoyed today's class, and I hope you'll recommend this video to your friends and your colleagues and your cousins and relatives. So do not forget to smash the like button and drop the homework answer in the comment section below. Okay, so take care, my warriors. See you again tomorrow. There is going to be a special session at 11 o'clock in the morning. Till then, take care, stay safe and stay healthy. Bye bye. Hasta la vista.